So it's interesting because Michelle here asked me, do you know Jamie Matthews?
Yeah.
Yeah, we do, because he's been here quite a few times over the years. And it was interesting because the last time he was here, he's saying, you really have to have Michelle Kunimoto as a speaker, because when I first met her as a student, she was a Star Trek fan. She still is, but now she's Spock. And I understand she got a telescope when she was a teenager and joined the RASC and did her first presentation to the RASC Vancouver Center when you was 17?
It was 2017.
2017. So, yeah, we're
So you need to say we're gonna get a lecture from an academic who's actually looked through a telescope.
actually look through it.
That's impressive.
That's impressive. What you don't realize is a few years ago, we had Dr. Ingrid Stairs here. And she was telling us about how she was at Gemini South
Mhm.
with two French astrophysicists. And she looked up at the sky and said, wow, isn't that an amazing sky? And they went, yeah, except for those two clouds. And she went, those are galaxies. They're the Magellanic Clouds. Anyway, I'll leave it to you now.
Thank you. I guess we'll just do a sound check to make sure everybody can hear me. Or do I need to move the mics closer? It's good. All right.
Yeah, good.
Awesome. So I like to start out with this picture of the Milky Way because generally when I give this talk in Vancouver, I make a joke about how there's a bunch of light pollution. You can't really see this, but since we're here on the lovely Sunshine Coast, you probably have a pretty nice dark sky here and you're able to look up at the night sky. So what I want you to think about is that our sun is a star and there are billions of stars in our galaxy. And just like how our sun has eight planets around it, every single one of those stars that you see the next time you go out probably has its own planetary system as well. And now that we've known about thousands of exoplanets, these planets outside of the solar system, we know that our universe is teeming with them. And there's a couple questions that I really like to address with the work that I do that motivates my research that I wanted to talk about to start off. The first question that really motivates my research is one that everybody here has probably asked themselves at some point in their lives. And that is, of course, the very big, are we alone question. Is there other life out there? Where might it be? If there is other life in our galaxy, probably exists on a planet that looks very much like our Earth. Now, the picture that I've chosen here is the famous pale blue dot, and it's a picture of the Earth taken from roughly around Saturn by Voyager 1 in the 1990s. And you can see the very small pale blue dot caught in the stray light from the sun. And I think this picture, better than most pictures, really captures that sense of curiosity we have and the desire we have to place our existence in context. But more generally, one of the things we can answer by looking at exoplanets is, how did we come to be? How did our planets in our solar system form and evolve? Is it really easy to form planets like our solar system, or are we rare? Are we very unusual in our galaxy? Now, this is getting into the physics of astrophysics because there are so many physical processes that dictate why some planets are more common than others, why we're able to form planets as small as the Earth and as big as Jupiter. So the way that I answer these questions is mainly through three different ways. The first one is by finding new exoplanets. The better we understand the diversity of planets outside of our solar system, the better we understand how common they are, what are their various properties. And once we find new exoplanets, we can also better characterize them, not just know about their basic properties, like how big they are or how far away they are from their stars, but we can actually peer into another exoplanet's atmosphere and understand the composition of the atmosphere and look for biosignatures. So I'm actually going to talk about how we can do that and how the James Webb Space Telescope has already been able to do some of that research as well. And more generally, once we have a lot of exoplanets, we can look for trends. Which planets are more common than others? How common are planets like our Earth? So I'll be able to answer that question here today as well. So let's go to that very first question. How do we actually find new exoplanets? Well, to start off, I'm actually going to take us on a bit of a history tour back about 5,000 years to 3000 BC. This is when the ancient Babylonians would have looked up in our night sky and they started to notice that there were these objects that looked a little bit different than those flickering light dots that you could see in the background. These are, of course, the very first planets we knew about in our solar system because they're naked eye objects. You could just simply look up, even without the aid of a backyard telescope, and be able to see them. And it's recordings of these very earliest objects that are one of the reasons why astronomy is considered the oldest science. These were recorded on clay tablets in as early as 2000 BC, and a lot of the history of planet hunting has evolved as well as the history of science. Now, it wasn't until a few hundred years ago that we started to find the first other planets in our solar system, and these ones were found with the aid of telescopes. In the 1950s were the first discoveries, or so-called discoveries, of exoplanets, but all of them turned out to be flukes in the data. We simply didn't have the technology or the know-how to really actually find planets outside of our solar system. And the reason is because these are planets that are extremely far away, many hundreds, thousands of light years away, orbiting much brighter, much bigger stars than these planets. And we can't simply look in a backyard telescope to find them. Now, I, of course, was not around in these early days of exoplanet astronomy, but I do have colleagues who were in the 70s and the 80s. And they talked about how exoplanets, being able to say that you could find a planet around another star, it was a total taboo topic. You would be laughed out of the conference, essentially, for even suggesting that you could find them. And all that changed in 1992. So I just want to pause for a second, because a reminder that planetary astronomy is thousands of years old. It's one of the oldest sciences. Exoplanets we've only known about for about 30 years, and it's now one of the biggest and fastest growing fields in astronomy. So Alex Wilson and Dale Frail completely revolutionized exoplanet astronomy by finding the very first exoplanets. So how did they do it? What I'm showing here is an animation of what's called a pulsar. This is a rapidly rotating radio star. And essentially, you can think of it like an enormous lighthouse beacon in space. Along two of its poles, it emits these radio waves. And every time that lighthouse beacon faces our Earth, we can record a pulse from that pulsar. And that's what you can see on the bottom left corner here. Now, these pulsars rotate so precisely that they rotate every few milliseconds or every few seconds, and they're so precise and consistent that they are considered the most accurate clocks in our universe. Now, let's say that we add a planet around this pulsar. Now, you might think of a planetary system as very simple, where we have a star completely stationary and all small objects like the planets are orbiting around it. But what really happens is that both of the objects, your planet and your star, are tugging on each other gravitationally. And so the star is actually wobbling very, very slightly around the center of mass of the system, just because that planet is gravitationally pulling on it as it orbits. So if you have a pulsar with a planet around it, at some point when it's wobbling around, it will be a little bit farther away from our Earth than at other times. And so those emissions are going to have to travel longer to reach us. And so when we're expecting the time of this pulsar to reach us, we'll be seeing it a little bit late, just because it's had to travel much farther. At other times, that pulsar will be a little bit closer to the Earth than at others, and that pulse won't have to travel as far, and so it'll arrive a bit early. So by simply seeing how early and how late these emissions are received by us, we can tell that there is some object in orbit around that pulsar causing it to be wobbling. Now, because pulsars are so accurate in how quickly they rotate, and how quickly they rotate, we're able to actually see objects as small as a moon mass around these objects. I do, however, want to point out a really important milestone in exoplanet astronomy that not a lot of people know about, but I want to get the word out because it has its own unique origins in our very own British Columbia. So 1988 was potentially the first ever exoplanet discovery. The reason it's not considered the first exoplanet discovery is because this planet was not confirmed as an exoplanet until 2002. So they weren't able to say they had the first confirmed exoplanet discovery. But it was actually made by a Canadian team of astronomers based at UBC and UVic. So Gordon Walker, Stevenson Yang, and Bruce Campbell found the very first exoplanet. They developed some of the best techniques that we still use to this day to find exoplanets out of UBC, which is really cool considering that's where I work now. And in doing so, they pioneered the second most successful detection method to date, which is the second one I'm going to talk about today. So this radial velocity method. What I'm showing you here is what's called a spectrum from a star. And it's essentially for our particular sun, it's all of the visible light that we receive from our sun. And so you can see that this light is split across many colors or wavelengths. You'll also notice that there are a lot of these black lines everywhere. So what these black lines are called absorption lines. Essentially, there's a molecule in our sun's atmosphere that absorbs light at this specific color or this specific wavelength. So as light is coming towards the Earth from the interior of our sun, it passes through the sun's atmosphere and it gets absorbed. And so we don't receive any light at these wavelengths because of the existence of one of these molecules. Now, it turns out that as the star is moving, these black lines actually shift a little bit. They shift to slightly different colors. So this is known as the Doppler effect, and you've actually experienced the Doppler effect if you've ever stood on a sidewalk and heard an ambulance go by. The frequency of that ambulance siren is going to change as it moves towards you and as it moves away from you. And so that's because the frequency of the sound waves are changing due to movement. So it's the exact same thing, but instead of an ambulance moving, it's a star moving because of the gravitational influence of an orbiting planet. So remember how I talked about how planets are causing their stars to wobble a little bit about the center of mass. So as a star is moving away from us, those spectral lines, those black lines are shifted more towards red colors. And as it's moving towards us, they shift towards more blue colors. So again, the same kind of science behind Doppler waves in terms of sound waves, but this is in terms of light waves instead. Now, I want you to pause for a second and think, just guess, kind of how small of a change of movement do you think that we're sensitive to for these stars? And remember that these stars are hundreds of light years away. Well, this technique is actually sensitive enough to tell a meter per second change in a star's movement. And the current latest generation of instruments have actually reached a precision of 20 centimeters per second. So we're able to tell that a star is moving by 20 centimeters every second due to the motion of an exoplanet orbiting around it. For context, Jupiter around our sun causes our sun to wobble about 13 meters every second. So this method is very capable of finding really big planets like Jupiter around other stars. Now, our Earth is much smaller than Jupiter, and it orbits pretty far away from our sun. And so it only causes our sun to wobble about 10 centimeters every second. So this is the ultimate goal of this technique, that we're able to see the change of another star's motion of only 10 centimeters per second. And over the next couple decades, we believe that we're going to get there. Now, there are a lot of different detection methods, and I'm not going to go over every single one. There is one more that I definitely want to highlight, but if you have any questions about any specific detection method, then feel free to ask. So after this very first exoplanet discovery rush, kind of in the early 90s, again, just 30 years ago, we started to realize it's possible. We can actually find exoplanets, and they're actually quite common. So this is a plot of the number of confirmed exoplanet detections as of about 15 years ago. And what I'm showing on the y-axis is planet mass. So really, really high mass objects are at the top, small mass planets like our Earth are at the bottom. And on the x-axis is orbital period. So that's how long it takes for a planet to orbit around its star. And what you can see is that the vast majority of these early exoplanet detections were really, really big planets, like planets much larger than Neptune. And specifically, there was kind of a class of exoplanets, which are known as the hot Jupiters. These are Jupiter mass objects that take only a few days to orbit around their stars. And because they're so close to their stars, because they're orbiting with very, very short orbital periods, they're going to be extremely hot. They're going to be bombarded by a lot of radiation. And so we call these hot Jupiters. Now, the reason why these are, well, one of the many reasons why these are so interesting is because if we look at our solar system, we have the 4 small planets relatively close and the 4 really big planets really far away. And we based all of our theories of planet formation off of our solar system for hundreds of years. And our theories of planet formation said you can only have really big planets far away from our sun for various reasons, like you have colder temperatures, and so you have more materials, icy materials, able to form bigger objects. And then these hot Jupiters come in and they kind of throw all of those theories out of the window, and we still to this day do not know why hot Jupiters exist. Our best explanation is that they did form like planets, giant planets in our solar system, and something moved them inwards to the places that we see now. But this is just an example of an early exoplanet detection that has significantly changed how we see planet formation. Now, you'll notice yeah.
When you invited us to ask questions, did you mean interrupt you?
You go ahead.
Okay.
Yeah, it's fine.
So would that be would it be fair to say, though, that it's quite probable that these Jupiters are not gas giants? Because if they were, the gas would be basically boiled up, if you will. They must be rock. Is that
Yeah,
true?
so that's a really good question. So if you're a roughly Neptune mass object and you're moved to these really short orbits, that does happen. You actually lose the atmosphere because they're irradiated so heavily that the atmosphere is stripped away. But you can actually still have a very, very gaseous planet that's as massive as Jupiter because it's so high mass that its gravity is really strong and it's able to trap its atmosphere and prevent it from escaping. So the hot Jupiters that we see today are really still have very, very thick atmospheres that look very much like the Jupiter in our own solar system. Yeah. Now, if you were to not have the plot legend here, I promise there are no planets below the plot legend. There aren't really any small planets that we saw in these early days of exoplanets. And again, this is just as of 15 years ago, we had no exoplanets that looked like our Earth. And I mentioned already that that's a huge motivation for looking for exoplanets. It's understanding our place in the universe. Now, all of that changed with the Kepler mission. So Kepler was NASA's first ever exoplanet finding mission, and it launched in 2009. And its entire goal was looking for other Earths around other suns, and to really answer that question, how common are planets like our Earth? And the way that it found exoplanets is using a technique known as the transit method. And this transit method is also how I look for exoplanets through my own work at UBC. Now, the basic idea behind this is that as we have a star, a planet's orbiting around that star, if it happens to pass directly between you, the observer, and the star itself, it will block a little bit of that star's light. So if you're measuring the brightness of the star over time, you'll see just for a few hours, that observed brightness is going to decrease for a few hours. And this is called a transit. Now, the size of the transit tells us something about how big a planet is, because a really big planet is going to block a lot of light, and a small planet is going to block only a little bit of light. We can also tell how long it takes for a planet to orbit because we can just measure the time between each transit. But planets are really small compared to their stars. If you were an alien trying to see the Earth transit our sun, which is basically us trying to find other Earths, you would need to be able to see a change of a star's brightness of only 0.008%. Now, I'm not very good at kind of understanding or visualizing these really small numbers. So there's an analogy that I like to use that I actually adopted from Jamie Matthews, which I find works really well. So what I want you to imagine is that you're looking at the Empire State Building in New York, and it's the dead of night, all the lights are on, all the window shades are up. Somebody closes the shades of a single window by just a few centimeters, and you have to detect the change of brightness from that motion from 100 kilometers away. And now consider that a transit is only going to happen over a few hours at a time. And if you're looking for another Earth around our sun, it's only going to happen once a year. So if you're looking for another Earth with this method, you basically have to look for years, recording the measurements of this star's brightness every, multiple times an hour just to see a few transits. On top of that, the orbital geometry for you to actually see a transit happen in the first place, for that planet to basically pass directly between you and the star, is really rare. A lot of planets will never even transit, and so we'll never be able to see them with this method. Again, if you were an alien observer trying to see the Earth transit our sun, the probability that the orbit would be just so aligned that you can do that is less than 0.5%. And so if you look at hundreds of stars for planets like our Earth, you might only see one or two. And recognizing all of that, this is kind of why the Kepler mission was designed as it was. It looked for planets around 150,000 stars to try to beat down on that transit probability, the fact that it's very, very rare that you'd ever see a transit. It looked for planets for 4 years, constantly recording the measurements of the star's brightness over time for that entire period of 4 years for all 150,000 stars. And it recorded a measurement of their brightness every 30 minutes to look for exoplanets. Now, the field of view of this telescope was relatively large for a telescope of its time. It's 115 degrees squared. That's about the amount of sky that you would cover if you were to hold your hand out at arm's length and cover it with your hand. At the time, it was the largest mirror ever sent into space, with a 1 meter primary diameter, and it was also the largest camera system in space. So in many ways, it was quite revolutionary. Now, Kepler was launched into an Earth trailing orbit in 2009. And what you can see here is that this telescope is constantly pointed to the left side of the screen. This is the Cygnus Lyrae constellation where all those hundreds of thousands of stars are lying. And you can see that it has these blue solar panels. And so for the telescope to be pointed at that same section of the sky all year round, while continuing to maintain power from our sun, it rotates on its axis by 90 degrees. So every quarter of a year. Now, just to give you a sense of how successful Kepler was, this is a plot of the number of new planet discoveries by their discovery year. And in blue are non-Kepler discoveries. In red are Kepler discoveries starting in that 2009. In 2014, they released their first major catalog paper. And they kind of blew everybody out of the water in terms of how many exoplanets they were able to release. And this was just their first of many catalog papers. They have since gone on to discover about half of all exoplanets that we know of today. This is just another view of it. This is the plot I showed you before of the planet masses versus orbital period. And the reason I said roughly 15 years ago, that's a very specific number because that's specifically before the Kepler mission. And this is after. So Kepler completely revolutionized how we saw small exoplanets. It was finally able to tell us more about planets that look very much like our own Earth. Now, Kepler unfortunately ended its mission early. After 4 years. It was supposed to last for many years longer, but nevertheless, it was an enormous success. It found about 2,700 confirmed exoplanets and another 2,000 candidate planets. So these are objects that we truly believe are likely planets, but for whatever reason, there could be another explanation in the data. We're not quite able to say that they're fully confirmed. But overall, 4,700 planets and planet candidates is an enormous success. Now, since Kepler launched and completely revolutionized the exoplanet field, there's been a lot of other missions that have launched. And one of them that I worked on actually for several years was NASA's Transiting Exoplanet Survey Satellite, the TESS mission at MIT. So this one was launched in 2018. It is still observing the night sky as we speak. And unlike Kepler, which looked at the same 150,000 stars for 4 years, just constantly staring and measuring brightness for those objects over all that time, TESS is an all-sky survey. It's basically trying to get measurements of every single star in our night sky, and it looks at each star for about 27 days at a time. So what you can see in this animation on the bottom is TESS's strategy for looking at the night sky. Essentially, it has an enormous field of view. It's basically a huge strip of the night sky. And it will look at all the stars in this strip, roughly about 1 million to 2 million stars any given month. It'll stare at them for every 200 seconds, recording the measurements of the brightness for 27 days, and then rotate to look at the next strip of sky. And after an entire year, it'll have mapped out 13 sectors. That's essentially half of our night sky. Now, since its launch in 2018, it has been filling in all the gaps left behind from previous sectors that weren't able to be observed, as well as re-observing stars that we already have data for. And it's been incredibly successful in finding a lot more exoplanets. Now, because TESS is an all-sky survey, it's telling us about how planets are distributed across our night sky. So what I'm showing here is a projection of our sky as you look out to it in a specific coordinate system. And you can see there's this very characteristic huge blob of planets here. That's those 4,700 planets and planet candidates from Kepler. And you can see a lot of other planets were found from mostly ground-based telescopes that have kind of been filling out some more of our night sky with exoplanets. TESS has found about 5,000 candidate planets and another 500 confirmed planets. And so just TESS and Kepler combined with the transit method, we know of about 3,000 confirmed exoplanets and about 10,000 candidates. Now, one thing I want to mention is that as part of the TESS team, and now at UBC, I run a lot of planet searches for TESS. and about half of them were found by my UBC-led faint star search. So it's been a lot of fun coordinating with the TESS mission and being able to find a lot of exoplanets for TESS. So what does that look like? What it actually looks like is not me, staring up at the night sky through a telescope, although I would really love to be able to do that to take the data that I do. But it means basically taking the data from TESS, downloading it onto my computer, and then looking at it. It basically kind of looks like this. So this is a particular star's light curve. It's the measurements of that star's brightness over time. And what I do is I run an automated algorithm that looks for those repeated transit dips that can tell us that a planet is orbiting around this star. So in this case, I would have picked out these two dips right here. I then look at the signal that could be caused by a transiting planet, and I ask myself, is this caused by a planet, or could there be an alternative explanation? For example, maybe it's not a planet that's blocking the light from another star. Maybe it's another star. It's a low mass star, or maybe a brown dwarf. Sometimes stars just randomly get brighter or fainter with time, and so we have to be careful when we find a possible transit that what we found is actually a planet. And a lot of this work is done through automated methods, but there's actually a lot of manual inspection that's involved that people around the world, high school students, amateur astronomers, are able to contribute to the TESS vetting process to identify these objects. So we've pretty much caught up to the present day, and so far we know of about 6,000 confirmed exoplanets. And as I mentioned before, the vast majority of them are from the transit method, and this is not including the roughly 10,000 candidates that we believe are real planets, but for whatever reason, they're actively going through follow-up so we can get a better sense. So really, we know of about 15,000 planets around other stars. And so this is an updated plot of that of what I showed you before, where we have planet masses on the y-axis, and on the x-axis, I'm showing orbital distance, so how far that planet actually orbits from its star. I've color-coded them by different detection methods, and so you can see that the transit detections are primarily within kind of the orbit of the Earth, 1 AU, 1 astronomical unit. That's the distance from our sun to us. And I've also colored in the planets of our solar system just so you can kind of place into context. Now you'll notice that there's an enormous empty region on the bottom right corner of this plot. Planets here exist. We know that most of the solar system lands here. It's just that we don't have the technology to find them yet. And I think that fact alone gives me a lot of excitement for the field of exoplanet astronomy, because it just shows how much more we have to discover about our night sky. But let's go over some major classes of planets that we know of so far. Now, I already mentioned the hot Jupiters, which were really exotic classes of planets that caused us to rewrite our planet formation theories. And even to this day, we don't have great explanations for how they can exist. We also have a large number of cold Jupiters, kind of analogs to our own Jupiter in our solar system. We also have planets as small as the Earth that orbit extremely close to their stars. So they orbit only within a few days. And what happens when you take rock and you heat it to really high temperatures? You start to get molten lava. And so we call these lava worlds. But the most common type of planet are planets that are roughly between the size of the Earth and Neptune. So these we call the super Earths, rocky planets slightly larger than Earth, and sub-Neptunes, which are more kind of gas-rich planets that look like mini versions of Neptune. These are an interesting class of planet because they are the most common type of planet that we've ever found, and yet our solar system does not have a planet in this size range. So the very fact that our solar system lacks the most common type of planet is actually another open question in exoplanet astronomy that we don't have a great answer for, but it's one of the ways that our solar system is actually kind of unique. We've also found planets around not just one star, but multiple stars. Now, the technical term for these is binary star planets, but we do actually refer to these as Tatooine worlds out of Star Wars. And we've also found planets that don't actually orbit any star at all. So these are rogue planets or free-floating planets. Now, if you look at the International Astronomical Union's definition of a planet, it does say that a planetary mass object has to orbit around another star to be considered a planet. So personally, I think that these rogue planets are actually planets. They may have actually formed in a planetary system like our own solar system, and then in the early chaotic days of formation got thrown out of their system through some kind of interaction, and are now freely floating throughout the galaxy, not tied to any system at all. And as I mentioned before, Planets here are just very hard to find for now, but we've got a lot of ways that we can improve our technology and find even more exoplanets and better understand the diversity of planetary systems. So we found a lot of exoplanets so far, and Kepler's entire goal was to find planets that look like our Earth. So what do I mean when I say Earth-like planet? Now, this is actually a series of criteria that I, as an exoplanet hunter, use to determine whether a planet that I found is potentially habitable, whether it could actually support life. And before I give this basic criteria, I do want to give an important caveat, which is that we have a single data point for a planet that can host life, which is our Earth. And you should never extrapolate from a single data point. That means that we're going to make a lot of very Earth-centric assumptions about what it means for a planet to host life. For example, we believe that life on Earth needs water to survive. And so another exoplanet that could host life also is going to need to host water. It's going to have to be rocky like our Earth. But there's a whole field called astrobiology, which tries to understand how exoplanet habitability could look like that's very non-Earth-like. So for example, in Star Trek, there was an episode with the Horta, a silicon-based life form instead of a carbon-based life form. So that is actually the topic of some astrobiology research papers. Can you have silicon-based life forms? And what would that look like on another planet? What about those that don't need water to survive, but could exist off of ammonia or methane? You know, those types of questions are a very real part of things that used to firmly be in the realm of science fiction, but are actually, part of the conversation today. So with that aside, let's go over kind of this Earth-centric view of how we define potentially habitable planets. So the first criteria is that we look at the size of the planet. Specifically, what we're wanting is a planet that is small enough that it is predominantly rocky, like our Earth, so roughly Earth size. Once you get too large, planets start to become more gaseous, like the gas planets of our solar system. And we don't believe that they're really able to host life like what we see on the Earth. That said, Carl Sagan is a really famous astronomer from several decades ago, and he actually wrote a paper that hypothesized gas bag-like jellyfish creatures that could exist in the gases of Jupiter. So, that could be possible, but again, we're going to focus on Earth-like habitability. Now you'll notice that I've put a lower bound on this planet size range as well, down to about 0.5, so half the size of the Earth. The reason why we don't want a planet to be too small, even though it will be predominantly rocky, is just because it will no longer have a high enough mass to actually sustain an atmosphere. Now, as I already mentioned, a mass is really important to actually hold on to an atmosphere. And atmospheres are extremely important for protecting life on Earth from radiation from the sun, from meteorites trying to hit the Earth, they can burn up in our atmosphere. So Mars is a good example of a planet that is not quite massive enough to host a sustainable atmosphere that's suitable for life. Second is the temperature of the planet. So specifically, what we're looking for are planets that orbit in their star's habitable zones. This is the range of distances from a star where a planet has just the right temperature to support liquid water on its surface. So just like how we also call this the Goldilocks zone, because the Goldilocks rhyme really works here. If a planet is too close to its star, it's going to be too hot, and any liquid water will just boil away. And if a planet is too far from its star, it will be really cold. Any liquid water can only exist in the form of ice. So specifically, we're looking for planets in that sweet spot where it's not too hot, not too cold, just the right temperature to support liquid water. And finally, we're really interested in not just the planet themselves, but what star do they orbit around? So specifically, we're looking for planets that orbit around stars very similar to our sun or smaller. There's a lot of reasons for this, but the main one is just how long does a star actually live for, and can that sustain life? So we believe that life on Earth took billions of years to develop, and so we want to make sure that that star is going to live billions of years. Otherwise, it'll explode, and we'll never be able to have life on this exoplanet. So the stars that are much bigger and much hotter than our sun, they go through their fuel really quickly. By quickly, of course, on astronomical timescales, I mean less than 1 billion years, which is really quick for us. But this means that they're never going to be able to let life develop safely on the planet. On the other hand, when you get to stars that are a lot smaller and a lot cooler than our sun, they don't go through nearly as much fuel because they don't have to maintain nearly as bright an object. And so they live a lot longer than our sun, and they provide this incredible, long-lasting environment where we could have exoplanets in the habitable zones. Now, one thing that's interesting about these classes of stars, these are also called red dwarfs or M dwarfs, is they're about 70% of all the stars in our Milky Way. They're the most common type of star. So if it can be that planets orbiting around these red dwarfs are able to be habitable, then they could be the most common habitable planet hosts. Now, there are a few issues with looking for planets around these types of stars I want to mention. So one of them is just that if you're orbiting around a star that is a lot smaller and cooler than our sun, it's like huddling around a really small campfire. You have to huddle a lot closer to that campfire to feel comfortable. And so any planet in the habitable zone is going to be really, really close to that star. As a result, you're going to be bombarded by a lot more direct radiation than what we're used to here on Earth. Now, of course, that doesn't mean that it's impossible that life can't survive in this excess radiation, but it is something that astrobiologists have to consider. Another thing that's interesting is that when you get really, really close to another star, that planet can actually be tidally locked, which means that the same side of that planet is always facing the star at all times. So our moon is an example of an object that is tidally locked with our Earth, which is why you only ever see one side of the moon. And so that means that one side of the planet will be in perpetual daytime and the opposite side will be in perpetual nighttime. And depending on how heat can distribute across the surface of that planet, it might be way too hot on one side and way too cold on the other to support life. Now, in science fiction, there have actually been books that are written about civilizations that live on the twilight zone that's just between the Earth, the perpetual day side and perpetual night side. So that is a possibility for life being able to exist. But more likely, we actually believe that if a planet has enough atmosphere, it can redistribute heat around the day side and the night side, and it can actually be quite habitable across the entire planet. Of course, if we were to find a planet around our sun that looks very much like our Earth, following these basic properties, these are our best chances for looking for life on another planet. So just to highlight a few real-life examples of planets that actually fall into this criteria. One of the most famous ones is the TRAPPIST-1 system. So this is a system of 7 rocky Earth-sized exoplanets. And if we were to place the TRAPPIST-1 system within our solar system, all of those 7 planets would actually orbit well within the orbit of Mercury. This is an extremely compact system. And because it is such a small, cool star, much smaller and cooler than our sun, the habitable zone is also a lot closer in. And there are actually 3 Earth-sized planets all in the habitable zone of this star. So this is actually a system that is very much under a lot of observation from the James Webb Space Telescope to actually understand the atmospheres of these exoplanets and hopefully look for signs of things like water vapor. And in fact, the very closest exoplanet to our own system, Proxima Centauri b, it is Earth-sized and in the habitable zone of its star. And so a lot of people sometimes ask me, do I have a favorite exoplanet? I would probably say Proxima Centauri b. And the reason is just because if our closest neighbor fits all of this criteria and is potentially habitable, I think that means that they must be everywhere. There is one exoplanet that is so far the one most like the Earth. This was found by Kepler, it's Kepler 452b. It orbits a star that is very similar to our sun. It's the exact same type of class of star. It has a year that's 385 days long instead of our 365-day year orbital period. And it's only 10% larger than the size of our Earth. And so it's firmly in that rocky class. So it's in the habitable zone. It orbits the same type of star as our sun. It is the closest Earth 2.0 we found so far. Now, because these planets are so far, we have a few dozen so far, but we're actually able to estimate just how common they are based off of our observations so far. And we found that about half of all sun-like stars probably host a rocky exoplanet in the habitable zone of these sun-like stars. So if there's hundreds of billions of sun-like stars in our galaxy, that could mean hundreds of billions of planets that look just like our Earth. And this is one of the reasons why I definitely believe that other life is out there in our galaxy. And especially when you start to consider there are trillions of galaxies in our universe, there's no way that we're alone. So let's say that we find an exoplanet and it fits all of this amazing criteria, and we want to actually know, can we tell that there is life on another one of these planets? Now, this is something that we've finally been able to start answering just within the last few years through some incredible techniques that I'm really excited to talk about. So when we find a new exoplanet, we want to characterize it better and understand it in more detail the properties that the transit method alone isn't able to tell us. So one of the things that we can do is look at a planet with a lot of detection methods. The transit method tells us how big the planet is because we can learn from the transit depth. The radial velocity method I have already covered tells us something about how massive the planet is because it's based off of the gravitational influence of that planet around a star. And so if you combine both mass and radius, you have density, and density is a really important proxy for composition. So we can actually tell if a planet has an Earth-like density, or if its density is predominantly gas-rich, so have very low density. And we can even tell if it has something, that can best describe all three of these variables as a water world. So a planet that is a rocky core covered by thick liquid water oceans, if it has a density that's appropriate. But more excitingly, and this is kind of something that we've only been able to do recently, is we can peer into another exoplanet's atmosphere and tell the composition. So this is a technique known as transmission spectroscopy, and it uses the transit method to do just this. So the idea behind transmission spectroscopy is that we have our planets, they have this opaque rocky core, and they also have an atmosphere. Our Earth, of course, has a very thin atmosphere. Jupiter has a really, really thick atmosphere. And if that planet happens to be transiting its star, the rocky core, the opaque part, is of course going to block all of that light, and the light can pass through the atmosphere of that exoplanet. But remember how I talked about that star spectrum, that beautiful array of colors, and there were those black absorption lines everywhere. That meant that there was some molecule in that star's atmosphere that was blocking light. And so if we were to look at that transit at a different wavelength, we would be able to see that at some wavelengths, more light is being blocked than others. So that transit depth is going to be deeper. So basically what this means is that if we were to look at a planet across many, many different colors, we can tell there's a molecule in that planet's atmosphere causing the size of the planet to look bigger or smaller, and then pin that to different molecules. So specifically what we want to do is look for biosignature gases. These are gases that could indicate the presence of life on another planet. So these are gases that are formed or produced by life or biological processes like water, carbon dioxide, methane, oxygen. Life is not the only reason why you can have one of these molecules in the atmosphere, but astrobiologists ask, is there a specific combination of these molecules that can only be explained by biological processes? Or is there a certain abundance of oxygen, for example, that can only be explained by life? Our Earth, for example, has a very oxygen-rich atmosphere. And the only reason we have that is because of life that formed very early on in our Earth's formation. So we're able to pin that and trace back the biological origins of all that oxygen. So ideally, we can start to do that for other exoplanets. And just as an example of a real world example of this technique in practice, this is a really cool discovery that happened a couple years ago, and we're still following up to this day. So the James Webb Space Telescope is NASA's flagship mission that is currently doing atmospheric characterization for a lot of exoplanets, for hundreds of them, especially those found by TESS. But this was a planet that is about 3 times the size of the Earth, and it is in the habitable zone. So it's not quite that small, nice Earth-like rocky size that I mentioned before, but based off what we know of its size and its mass and its density, we believe that it's an ocean world. So it's a thick, it's a small core covered by a thick layer of ocean. And James Webb used this technique to look at the atmosphere of this exoplanet and found methane and carbon dioxide. So we already have 2 biosignatures. But more excitingly, there was a possible detection of a molecule called dimethyl sulfide, or DMS. On Earth, it is only produced by life. And specifically, it is only produced by phytoplankton in Earth's oceans. And so if this is an ocean world and we have detected DMS, this could actually be the first evidence for life on another exoplanet. Now, the researchers, of course, were very cautious. You don't want to make this huge claim that you found life on another planet without being totally sure. And so they wanted to emphasize that it is a possible detection. There could be other explanations. And James Webb has been actively looking at this exoplanet to get more data to see if that signal gets stronger or can be explained by something else. But regardless of what this turns out to actually be, I think the very fact that we're having this conversation, that we can actually say that we've possibly found life in another exoplanet just because of its atmosphere is really, really exciting. So one last thing I want to mention is one of my favorite things about exoplanet astronomy, which is related to the fact that anybody can get involved. Now, I got involved with exoplanet hunting as young as an undergraduate, but people as young as high school have been able to find exoplanets. And one of the reasons is because exoplanet astronomy, the data that we use is publicly available and anybody can get involved. So one example is that you can actually download all of Kepler's data and TESS's data from the Mikulski Archive for Space Telescopes. There's also a lot of resources on the internet for finding and analyzing transit signals automatically. So if you have enough coding experience, or even if you don't and you want to start learning, there's a lot of resources that people have written and have just simply used open source code to be able to find exoplanets. And this is how I, as an undergraduate student, started my own planet searches. I essentially just downloaded random light curves from the Kepler dataset, downloaded some random code that seemed to be relatively user-friendly, and I had no coding experience at this time, and I was able to find 4 planet candidates. And then, of course, since working on the TESS mission, that number has become about 3,500. And if you don't want to use any programming at all, and you simply just want to use your internet browser, there is also options for you. So this is a website called Planet Hunters TESS, and it's a citizen science initiative. The idea behind Planet Hunters is that humans have a remarkable ability for pattern recognition. And in many ways, we're better than some of the automated algorithms that look for exoplanets. The downside, of course, is that we're not nearly as fast as these automated algorithms, but nevertheless, we're pretty good at finding things. And so they've uploaded hundreds of thousands to millions of light curves from the TESS mission that you can just by eye go through and try to find transits. They've actually found hundreds of planets that were missed by official teams out of NASA, out of MIT, just around the world. And some of them have been some of the strangest light curves that we've ever found, just showing the power of citizen science. Again, all you need to know is what a transit looks like. It's a dip of brightness that occurs periodically, and you need an internet browser. And that's pretty much it. So one of the most cool discoveries was in about 2018. Some of you may remember this, but there was a discovery of the star that caused these really wild changes of brightness that nobody knew how to explain. And there was actually a paper that came out from the astronomy community that tried to explain it, that said it could be caused by a Dyson sphere made by an alien civilization formed around this star. And the reason why we have all this weird, random changes of brightness is just the structure itself is blocking light from that star as it rotates. Now, we believe that it's probably more likely just a cloud of comets around this star, just disintegrating and kind of changing in their brightness over time. But this was something discovered by citizen scientists. If it wasn't for citizen scientists like Planet Hunters, we would never have better understood this system. And again, they have found hundreds of exoplanets. So some last thoughts as I wrap up here. Exoplanet hunting has really exploded in the last few decades. Again, we found the very first exoplanets in 1992 or 1988, depending on your definition of the first exoplanet. But exoplanets is such a young field, and it shows no signs of stopping. Now, Kepler and TESS are kind of the most popular telescopes that we've been using to find exoplanets, but there's a couple more that are going to be coming just over the horizon that are going to find even more. So one of them is the Plato mission. This is a European Space Agency mission that will hopefully launch next year, and it will do something similar to Kepler. It will look at the same section of the sky, measure the brightness of those stars over time to try to find other Earths around other suns. There's also NASA's next flagship mission, the Nancy Grace Roman Telescope, hopefully going to launch next year, probably 2027. And based off of some yield calculations of the Nancy Grace Roman Telescope, it's going to find 200,000 exoplanets. So we've already been kept busy with our small 5,000 number, and we're really not going to know what to do with ourselves once Roman launches. And in fact, if you look at the state of exoplanet astronomy in the coming decades, the future is really, really bright. So there's a decadal survey. It's essentially a survey of the international astronomical community every 10 years. And it asks, what do you think should be the highest priority for astronomy in the US? And the results of this decadal survey are directly used to inform which flagship mission should NASA fund, right? So we've had Hubble in the past, we have the James Webb Space Telescope currently, we have the Roman telescope coming up. What about the next really big multi-billion-dollar flagship mission? And astronomers loud and clear said that the search for habitable worlds should be the top priority for astronomy. And as a result, the exoplanet scientists won. As we said, when we found out the news that the Habitable Worlds Observatory was selected as the next flagship mission, we were very excited. So this is a telescope that is actually going to directly image other Earths around other suns in the habitable zone. And on the top right corner, you can see a real exoplanet system that has been directly imaged. So these are actual pictures of other planets orbiting their stars. Now, of course, the star in the center has been blotted out because otherwise it would just be way too bright for us to be able to see it, to see those little planets, very much like trying to spot a firefly flying around a lighthouse beacon. But this is actually going to be able to find other Earths. And by doing this in different wavelengths, we can see how bright does that planet appear in different wavelengths and be able to measure the signatures from these biosignature gases. So hopefully the Habitable Worlds Observatory will launch in roughly the 2040s. And right now there's still plans to design just how big of a telescope we need to be able to do that. And as we find all these new exoplanets, our perspective of planets in the Milky Way has constantly been changing. We've gone from those exotic hot Jupiters, we found Tatooine worlds, we found rogue planets. Only the first 3 rogue planets ever found that are low mass like our Earth have been found just in the last few years. So this is a whole population of planets that we know very little about. And of course, we continue to search for these other Earths, hopefully planets that meet our basic criteria for what it means to be potentially habitable. But as we understand more about how life could exist on another planet, we might start to change those definitions and start to open up the possibilities for how life can exist on another exoplanet. And one of my favorite things about exoplanet astronomy is really that anybody can get involved. Again, you just need your internet browser and some time and some interest in contributing to science, and people have made some incredible discoveries. And it's one of the things that I'm proudest about my field. So with that, I will take questions. Thank you.
The graph that you showed of planet mass versus orbital radius, it had a big black hole in the lower right corner.
Yeah.
What's needed to fill in that black hole? Is there like a different kind of technology that we have to pursue to fill in that black area?
Yeah, so part of it really depends on the technique that you use to find an exoplanet. So as one example, if we look at the transit method it has the best precision to find really small planets, but it's reliant on how long it takes for us to actually look at a star. Because we can't find planets that orbit, every thousands of years, for example, because we don't have surveys that can last that long. So part of it is that we're limited by just how long we're actually looking at the night sky. Now, there are some techniques that are able to find objects that are really, really far away. And essentially, it's just bigger telescopes, better technology. We're able to see smaller and smaller objects. Now, I will mention that Roman is going to use this gravitational microlensing technique that I didn't talk about, and it's actually expected to reach all the way up to about here across all planet masses. So this is, it's just bigger telescopes, especially in space, have better precision, and we're able to push that down.
Same as opposed to the radical new technology or.
Yeah, well, so especially with the direct imaging method, there have been some advancements in the specific technique. Like there's different ways to blot out the star's light, for example. So the technique that I showed with kind of that animation used something called a coronagraph. But there's alternative technologies that people haven't even tested yet, but might be able to do a much better job and see even smaller exoplanets. So most of it I think is just bigger telescopes give us better precision, and it's expensive and takes a really long time to make such big telescopes. But to a lesser extent, it's definitely the actual techniques that we're using. But in terms of the basic techniques to actually find exoplanets, I think we're at a pretty complete point about like the transit method, rate of velocity, microlensing, direct imaging are really going to be the big four techniques as we move forwards.
Could you explain the microlens?
Sure. Just in case I got a question about this, I put together a supplementary slide. So the reason I didn't talk about this is because it involves general relativity. And it's one of the harder ones to kind of wrap your head around. Okay, so I'll do my best. So the idea here is that we have a mass, and mass actually bends space around it. And so what happens is that if a planetary mass object like a rogue planet passes in front of a really background star, and it passes perfectly, like there's a perfect alignment, it passes directly between you and the observer. The space that's being bent will cause the light from that background star to be bent around your rogue planet. You can see here. And so it will actually look like the star is coming from two different places. And so what this causes is actually a brightening effect. It's called a lensing effect. It will cause this background star to be imaged onto two images and basically look a lot brighter than it actually is, just through this imaging onto this what's called an Einstein ring. So if you're measuring the brightness of a faraway star over time, what you're not looking for is decreases of brightness caused by transits. You're looking for increases of brightness caused by microlensing events. So one of the projects that I've actually started just in the last year is to use the TESS mission data set to look for microlensing events, because it's really good at finding really tiny changes of brightness caused by transits. And so you'd think that it would also be good at finding really tiny increases of brightness caused by microlensing. And I actually might have found TESS's first rogue planet candidate, which I've got a paper in the review process to talk about. But this is a real life like signal that what it might look like in our data is this tiny bump that happens only once and will never be able to be observed again.
So that's in the case of a rogue planet.
Mhm.
But in the case of a planet that's in an exoplanet that's in orbit around another star, could this technique be used to pick that up?
Yeah, so in that case, because the planet and the star will be so close, you'll see one lensing event from the star mass bending space, and then a tinier increase due to the planet mass bending space. So we call those a binary lensing event. You'll see two increases of brightness, one caused by the primary stellar mass and one caused by the planet mass. Now, planetary mass microlensing events, like those caused by these low mass rogue planets, they take place over a few hours. Stellar mass lensing events can take place over months. So the scale of them is very different, and that's how we can know that it's a small object orbiting a big object. Yes.
I have actually two questions. One, you mentioned transits
Mhm.
and the radial velocity shifts. Both of those, you get a signal or the strongest signal when the plane of that orbit, Earth is in that plane.
Mhm.
Now, since it's perfectly reasonable to assume that orbits are distributed randomly.
Mhm.
If you're looking at a teensy little star with big orbits of planets, you've got a tiny fraction
Mhm.
of potential star planet systems where you do get a transit.
Mhm.
And if that were 1 in 1,000, if you were to see 2 in 1,000, just doing general surveys, the odds are there's planets everywhere.
Yeah. Yeah. So actually, a big component of the work that I do is to do that type of statistics, like to understand if you have a 0.5% chance of seeing a planet directly pass in front of a star and cause a transit, then any one detection represents 0.5% of all planets that are of those properties. And so once we understand our biases and in how, we're going to be able to only see the transiting planets and only the ones that cause big enough transits in our data, then you can correct for those biases and basically reveal the underlying population of planets. So even though our observations of millions of stars have resulted in only 4,000 planets, we can tell based off of the low probability of finding one of these that planets are actually on average, multiple planets for every star that you see in our night sky, that planets really are everywhere. There's hundreds of billions of them.
Second question is, I'm sure you thought of this. What are the odds of them naming one of them after you?
I-
'Cause I would think that if I were you.
Yeah, well, so there are some planets that are passed around by the International Astronomical Union to get special names, and typically these are names that are drawn from science fiction, and or just, you know, culturally significant names. I don't know of any that have been named after a person, but maybe one year that will be, yeah.
When you're using transit, of course, it has to go right across the face of the sun,
Yeah.
star. But if you're using radial velocity, that could be above or below the plane and still have a measurable effect. Has there been any kind of like sort of study of that connection?
Yeah.
To see, you know, to sort of kind of open up the window.
Yeah, that's a great question. So as you mentioned, with transits, we're basically completely constrained to looking at what we call edge-on systems. They're planets that orbit, you know, basically in this plane. Radial velocities, we can start to see planets that are inclined basically everywhere until you get completely face-on, when there's no radial shift in the star's movement. So when we're actually measuring a planet's mass with the radial velocity method, we're actually measuring the minimum mass possible, because we typically don't know what its inclination angle is. Because if it could be that it's a planet in an edge-on orbit, in which case we're seeing the maximum radial velocity shift. But if it's close to face-on, we're only seeing a small component of the star's radial velocity, and therefore that radial velocity signal will be very small. So there are other techniques, though, that actually want to look for exoplanets in a face-on orbit. So direct imaging is an example of one where we can't actually pick out, you know, that planets are orbiting another star with direct imaging if they're completely edge-on. But if they're face-on, you know, it's really easy to see the planets distributed. So there are some techniques that are better at seeing face-on planets. Some are better at finding edge-on planets. And in terms of our understanding of how orbits are inclined, we typically adopt that they're just completely random. Like there's no specific geometry that's favored over another. They're just, the inclination angles are all completely uniformly distributed.
Random from like one, like obviously
From,
planets around
yeah.
the sun are all very close to the same plane.
So planets in the same system are typically coplanar, which means they all orbit in the same plane. But if we're looking at a random system far away, that plane can be any orientation.
And they were explaining that when they designed Kepler, they based its sensitivity on our yellow dwarf.
Unfortunately.
Unfortunately, because when they got up there, they discovered most yellow dwarfs are a lot more active than
Yeah.
our sun is.
Right. So Kepler designed the telescope and chose like the camera system and the size of the telescope in order to be able to find exoplanets that are the size of the Earth around other sun-like stars. And in order to do that, it needed an estimate of how noisy the light curves would be so that we could pick out a transit depth relative to that noise. And they based the estimate of how noisy sun-like stars are based off of our sun. And it turns out that our sun is an unusually quiet star. And if you look at a random sun-like star, they're a lot noisier. And so all of the numbers that they estimated for how the precision that you would need to find exoplanets was totally off. And that's one of the reasons why Kepler was not as successful as it hoped to be. It was actually supposed to be able to find many more Earth-like exoplanets, but because its design was incorrect, it didn't find as many as we hoped. So technically, now I don't say this, but I have a friend who worked on the Kepler mission, and according to him, Kepler was a failure because it did not meet its primary mission goal of finding a confirmed Earth-like planet around a sun-like star. There was that Kepler 452b I mentioned, but it's so close to the noise that some people are concerned that it's actually a transit. And if it had not gotten those calculations wrong, maybe we would be, maybe it would have been a success. Well, I of course consider it a success because it found thousands of objects and is continuing to revolutionize how we see exoplanet astronomy. But yeah, it was a little bit off, those numbers. Combined with the instrumental failure that ended the mission at 4 years instead of 8 years. Yeah.
Well, we've only got one data point.
Yeah.
Yeah, work with it.
Yeah.